So remember this problem of giving cookies to children, right? So you have n cookies and you have k children. You want it, and all the cookies are identical, right? And you wanted to break them up and give them to the children. You want to count how many ways there were to do that, right? And the answer was n minus 1, choose k minus 1, if you wanted to give at least one cookie to each child. Now, giving 3 cookies to the first child and 4 cookies to the second child, or giving 4 to the first child and 3 to the second child, those are different things, right? In that problem. But what if instead of giving cookies to children, where children, every child is different, what if instead we want to put cookies into boxes where we can't tell the difference between 2 boxes? So the boxes are all identical. So imagine these are just these like plastic boxes that they put cookies in at the grocery store or whatever. So I want to put, identical cookies into any number of identical boxes. And I don't care which cookie goes into which box because all the boxes are the same. All I care about is how many cookies go into the boxes. So if I put 2 cookies in the first one and 1 in the second one, that's the same as putting 1 in the first one and 2 in the second one. Because I can't tell the difference because I could just switch the boxes and it's all, it's the same. So to be clear, or I'm not sure if it is clear or not, but so let's think about the case n is 2. So n is the number of cookies, and let's say the number of cookies is 2. So I claim that the number of ways to distribute the cookies is 2, right? So either both cookies go into the same box, so that's one solution, or you have the second solution where the cookies go into 2 different boxes, okay? Now, things get a little bit more interesting when you go to 3. So suppose you have 3 cookies. How many ways can I separate them into boxes where the boxes are all identical? And I claim that there's 3 ways to do it. So the first way is that I can put all of them into the same box, okay? Or I could use 2 boxes. I could put 2 into one box and 1 into the other. Or I could use 3 boxes and I could put 1 in each. Okay, and notice that the answer here is 3, not 4. So if I switch these 2 boxes, I consider that the same solution because I can't tell the difference between the boxes. Is it clear what I'm saying here, that there's 3 solutions, not 4? So if I put 1 cookie in the first box and 2 in the second one, I consider these to be the same thing because I could just switch the boxes and I wouldn't be able to tell the difference. So we want to distribute these identical cookies into identical boxes and we want to look at how many ways can I do that. And all I care about is how many cookies end up in the boxes. So just to see if we understand this, let me give you a poll. So how many ways, suppose I've got 4 cookies, how many ways can I do it? Okay, we're getting only a few answers so far. Feel free to give your opinion on this. The answers seem to be kind of clustering around a few different values. So is there 4 ways to do it, 5 ways to do it? Some people maybe think there's 6 ways to do it. So, okay, well, let's kind of work it out. So if I want to put them all in one box, I have, there's only one way to put it in one box. I just put 4 in one box. If I wanted to put it in 2 boxes, I could put 3 in one and 1 in the other. If I put 1 in the first box and 3 in the second box, that's the same thing. That doesn't count as different. So I don't count 1, 3 because that's the same as 3, 1. I could put 2 and 2. That's different. If I use 3 boxes, there's only really one way to do it with 3 boxes. I could do 2, 1, 1. Because if you think about it, any other way to use 3 boxes is going to be the same as 2, 1, 1. And if I use 4 boxes, I've got 1, 1, 1, 1. So 1, 2, 3, 4, 5 ways to do it. So the answer is 5. Okay, is that clear? Any questions about that? Did I miss one in particular? Okay. So, so this brings us to the next topic, which is integer partitions. So an integer partition is a way of writing an integer n as a sum of numbers, a1 up to ak, where a1 is at least as big as a2, which is at least as big as a3, at least as big as a4, etc., down to ak, which is at least 1. So all the numbers are at least 1, and they come in decreasing order. And I say that So the number, or I guess the notation I'll use for a partition is just, I just write the sum. So I would say that A1 plus A2 plus dot 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 up to AK is a partition of n. So for example, if I look at 4, the number 4, how many partitions are there? Well, I could take just 4, the number 4, right? I just take A1 equals 4, or I could take A1 is 3, A2 is 1. So I take 3 plus 1, or I take 2 plus 2, or so those are all the partitions into 2 parts. So I call these things, by the way, these are called parts of the partition. So these are, all parts. If I want to break 4 into 3 parts, I have 2 plus 1 plus 1, and that's the only way to do it. Or I have 1 plus 1 plus 1 plus 1 into 4 parts. And if you think about this, this is the same as this cookie question, right? Because all we cared about was how many cookies are in each box. We didn't care about switching the boxes, right? So actually, if you look back on the previous slide, these are basically writing out the partitions of 4. So I've got 4, I've got 3 plus 1, 2 plus 2, or 2 plus 1 plus 1, or 1 plus 1 plus 1 plus 1. Okay, so the number of solutions to this cookie question is equal to the number of partitions of n. Okay, so partitions of 5. So there's, I could do 5 or 4 plus 1 or 3 plus 2 or 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, or 5 ones. So there's 1, 2, 3, 4, 5, 6, 7 of them. So is it clear what a partition, an integer partition is? Any questions about that? Yeah, so this is just kind of recapping what I said. So the number of ways to put n identical cookies into identical boxes is the number of partitions of n. And the notation we're going to use for this is Pn. Now, there's a bit of ambiguity if I talk about P0, like how many ways can I put 0 cookies into boxes? Just for convenience, it's going to be useful to think of P0 as being 1. Okay, so don't worry too much about P0, but just remember that P0 is 1. So the number of partitions of 0 is 1. If anyone ever asks you, it's 1. Okay, even though, yeah, maybe you could think there's 0 partitions of 0, but let's just think of it being 1. Okay, so Pn is counts the partitions of n. So there's a nice way of representing a partition, which actually is going to immediately give us a theorem by just kind of understanding this representation. So a Ferr's diagram is an arrangement of n dots into rows so that every row, if I take the top row, okay, the top row has the most dots. The next row has at most as many dots as the top row. The third row has at most as many dots as the second row, and so on. So each row has at most as many dots as the row that came before it. So in total, you have n dots, and yeah, you kind of arrange them in rows in this way. Now, I think it's kind of clear that this is the same as a partition, right? Because so if I write down a Ferr's diagram where I have 4 on the top, I have 2 on the next level, right? So a Ferr's diagram, you have to have, every row has to have at most as many as the previous row, but it could have the same number, right? So I could have 2 here, and I have 1 here. Now it's kind of clear that this is the same as a partition of the number 9, because I've got 9 dots. If you add up 4 plus 2 plus 2 plus 1, it's 9. And this corresponds to the partition 4 plus 2 plus 2 plus 1. Okay. But so note that we do this by rows. So the first row is the first number in the partition, not the first column. Let's do a poll just briefly. So which partition corresponds to this Ferr's diagram? So it's going to be a partition of 12 because in total you can see that there's 12 cookies. Okay, and by the way, yeah, usually if you see a Ferr's diagram, they do that with dots, right? I don't know. I decided I'd already made this picture of a cookie, so I thought may as well do cookies. But yeah, if you look in the textbook, you won't see cookies. So think of these cookies as dots. But yeah, I think it's unanimous that everyone's got it. So it's going to be 4 plus 3 plus 2 plus 2 plus 1. So the only way that you could, I think, be confused on this is if you mixed up the rows and the columns, right? Because if I did it by columns, I would see So yeah, so this is the answer, 4 plus 3 plus 2 plus 2 plus 1. If I did it by columns, right, you could get messed up. So don't forget it is by, you do the rows, not the columns. The columns would give you 5 plus 4 plus 2 plus 1, right? Which is a different partition. But actually this observation about rows and columns is kind of gives us something interesting because, I mean, the number of rows is the number of parts in the partition, right? The number of columns is the biggest number in the partition. If you kind of take a transpose, like if you know, I don't know if people know kind of matrix transposes, but if you kind of take this picture and you flip it over the diagonal, you change the rows to columns and the columns to rows, then you get another partition of the number 12. And this is the kind of a bijection between different types of partitions. So it's a kind of one-to-one correspondence. So let me kind of explain this more fully. So the thing I want to tell you using Farrer's diagrams is that the number of partitions into k parts is equal to the number of partitions. So this is a partition of n. So number of partitions of n into k parts is equal to the number of partitions of n such that the largest part is equal to k. And the proof is just to take a Farrer's diagram, right? The number of rows in a Farrer's diagram is equal to the number of parts in the partition. So if we're dealing with partitions into k parts, then it will be equal to k. The number of columns is equal to so if you think of the number of columns here, it's just equal to what is the biggest element. So it's equal to the size of the largest part. If I take the Farrer's diagram and I flip it diagonally, in other words, so flipping it diagonally is the same thing as saying I look at the first column, which has 1, 2, 3, 4, 5 things, and I write it as a row. I take the second column and I write it as a row. I take the third column, I write it as a row, and the fourth column, I write it as a row. If you flip it this way, what's going to happen is the number of columns in your original partition or Farrer's diagram will turn into the number of rows, and the number of rows will turn into the number of columns. So this gives a one-to-one correspondence between Farrer's diagrams where the number of rows is k and Farrer's diagrams where the number of columns is k. In other words, it gives a one-to-one correspondence between partitions where the number of parts is k or the largest part is k. Any questions about this? Okay, so here's what we're going to do next, which is to come up with the generating functions for partitions, which is a little bit tricky. So I want to find out what is the generating function for Pn. Okay, so on one hand, it's pretty easy because I can just write that it's a sum n equals 0 to infinity Pn x to the n. Okay, but that's not very useful. So I want to have a kind of more useful way of writing the generating function. So let's think about a partition of n. So let's say I let x1 be the number of ones in the partition, x2 is the number of twos, x3 is the number of threes, and so on up to xn, which is the number of n's. So what kind of equation can I get involving these things? So I want to put a coefficient in each of these green blobs. And I want to say that something times x1 plus something times x2, something times x3, all the way up to something times xn is equal to n for any partition of n. So if you think about it, the coefficient I want to put before each of these things is equal to the index. So if I take x1 times the number, I take 1 times the number of ones plus 2 times the number of twos, 3 times the number of threes, up to n times the number of n's in the partition, this equals n, right? Because, yeah, for example, if I'm taking 1 plus 1 plus 1 plus 2 plus 3 plus 7, so that's 1, 2, 3, 4, 5, 6, 7, 8, 15. So in this example, I would have x1 is 3, x2 is 1, x3 is 1, x7 is 1, and all the other x's are 0. And if you check, you'll see that 1 times x1 plus 2 times x2, 3 times x3 plus 7 times x7 is equal to 15. And here implicitly I have a 0 because for all of the other terms, because there are no other terms, right? So all of the other xi's are 0. And anyway, so right, so is this clear? So partition equal to the number of, solutions to this equation, number of partitions of n. Okay, so using this, I want this to help me get a generating function for Pn. Okay, so this is a little bit of a leap of logic here, but I need to, so I'll try to justify this. So I claim that the function for Pn is like this. You take 1 plus x squared, x cubed, etc., off to infinity as my first factor. Okay, and here the exponent that I choose will correspond to the number of ones in the partition. So using the notation from the previous slide, this is like the exponent chosen here is my corresponding to my x1, or 1 times x1, if that makes sense. Then I have 1 plus x squared plus x to the 4, etc. The exponent that I choose here to correspond to my x2 in some sense. So the exponent here is going to be my 2 times x2, or like it corresponds to the number of 2's I take in the partition. And the exponent here that I choose corresponds to my 3 times x3, and my exponent here corresponds, to my 4 times x4, right? And we want 1 times x1 plus 2 times x2 plus ... up to n times xn to equal n, right? And here I've got a ... thing because we do this, we keep this going. So we have the next factor is 1 plus x to the 5 plus x to the 10, and so on. Okay. So if you think about it, it's a little bit maybe tricky to conceptualize this, but if you think about your coefficient of x to the n, the coefficient of x to the n will be equal to the solutions to this equation here, this equation, which we've argued is equal to the number of partitions of n. Now, of course, we know how to simplify this, or I'm not sure if it makes it simpler or not, but the first term we can write as 1 over 1 minus x. The second factor is just 1 over 1 minus x squared. Then you have 1 over 1 minus x cubed, x to the 4, x to the 5, and so on and so forth. So this is just the product of, so I'm not sure, are you guys familiar with this notation, this product notation? Yeah? So this is, all I'm doing here is, this is just rewriting this. It's just the product. Okay. So let's say, it's kind of like summation notation. Like, if I write sum of n equals 1 to infinity of an, right? That's just the same as a1 plus a2 plus ... If I write the product, n equals 1 to infinity of an, it's like the same thing as the summation notation, except instead of summing, you multiply. So that will be a1 times a2 times a3 times ... all the way to infinity. So all I'm doing here is I'm rewriting, just because it's a bit, this ... is a little bit not that formal, just a little bit more formally. I'm just rewriting this like this. So the product, m equals 1 to infinity of 1 over 1 minus x to the m. So it just means the same thing as this. You take m equals 1, so that gives you 1 over 1 minus x. M equals 2, that gives you 1 over 1 minus x squared. And then you just multiply them all up. So this weird thing is the generating function of partitions of n. And yes, it is a kind of a weird function. And it's kind of also kind of a nice function, but even though it does give us a generating function for partitions, in some sense, it doesn't actually make it easy to compute Pn. So this whole time we've been dealing with generating functions, right? And the great thing about generating functions has been that it allows us to compute numbers. In this case, this generating function isn't very good for computing Pn, unfortunately. But nonetheless, it is a generating function for it. But I should say that even kind of getting a rough idea of how fast Pn grows, that's a very hard problem. So I think in the textbook, it even mentions that in the movie, The Man Who Knew Infinity, which is a movie about Ramanujan. This is one of the things that comes up in that movie. So it's a very hard problem. This is a good question. So why is m from 1 to infinity not 1 up to n? So a partition of n can only have n parts, right? But we're trying to, so this is supposed to count the partitions of n for every n. So yeah, so if I was just writing, um, so because this is trying to count partitions of n for every n, you have to go up to infinity. So this is not for a specific value of n. So here we're looking at every possible value of n. Now it's true that if I say I have like n plus 1 parts or something, or parts of size n plus 1, it's impossible to make n out of parts of size n plus 1. But that will, if you think about the coefficients, that's actually kind of implied by this formula. So it's, yeah. If you think back to this thing, if I take n plus 1, like the coefficient of n, x, so if I take my x sub n plus 1, it has to be 0 if I'm making n. Anyway, it's, yeah. I think thinking about how you get x to the n from these factors is useful.